So this is part 2, lecture 3 and 4, of an overview of tools in machine learning. So this is lecture 3 and 4, and I want to say a few words about just in general why I chose these topics and so forth. I tried to pick things in constructing these lectures that I thought might have been told to people with coursework maybe, but it's very hard to get such things, so some of you will learn this stuff in your time. So then I also tried to think back and think, what kind of stuff intimidated me when I learned it first? Maybe I could try and explain it. Think of the kinds of things where I would love to have had somebody pull me aside and say, this is how this works. So I wanted to try and reflect stuff like that. There's obviously some major gaps here. There's nothing on probability theory. There's nothing on information theory. Those would be lectures 5 and 6, I guess. 5 and 6. So necessity, there will be some slides where it seems to be trivial, and other slides less so. So we'll just view the obvious stuff as little intellectual breathers before you get to the less obvious stuff. So today we'll do major theorems, a few notes there, and complex optimization. Alright, let's start very basic stuff. You probably all know this, but it's just to warm up. So suppose you have an orthogonal basis in Rn. So you've got a bunch of n vectors, they're all orthogonal and beautiful lines. Now, I've just used MATLAB to create 3 orthogonal vectors, for example. Is it necessarily true if I do that, I just choose 3 random orthogonal vectors that the relative statistics are also orthogonal? Is that always the case or not? Well, actually, yes, it is always the case. So I'm going to introduce these. I've introduced the matrix here where the columns are labeled by I in parentheses and goes by A. And so VI by the APJ is spelled with here. So I'm going to introduce vectors I call dual basis. And you can do the dot product between rows now. Well, I just switched the names of the vectors for their indices. That's how I define these dual products. Weird, but I did it. So I want to keep this dot product. And if you just write out what this is, it's n, k, I, and vi. By the way, when you see repeated indices, it means like sum. And this I otherwise say, it's very useful convention. And that's n transpose to a, b, o. We do know that this is true because we know that the e's are orthogonal. But is it necessarily true that this is delta a b? Well, this is full rank, so it has an inverse. So I'll apply the inverse to both sides. And that then gives you n inverse is equal to transpose. Then, because I know that every matrix has a unique inverse, and I also know that the left and right inverse of any matrix is the same thing always, all theorems, it must be true that there is transpose. So yes, indeed, if these guys are all orthogonal, then of necessity, so are these different orthogonal bases, which is true for any orthogonal set. We'll call that dual basis. How is this useful? Well, you're doing some deep calculation in learning theory, and you come across a sum you wish to compute. But it's not summed over the indices of your vectors, it's summed over the vectors themselves. But happily, because you know that this is true, you can just replace this by dot by j, this sum goes away, and on you go with your calculation. Okay, it's one little trick. Second, again, stuff you probably know, so moving up here. Matrix multiplication. Everybody knows how to multiply matrices. I have a matrix and n, and then another one that is b, and I compute the product this way. So this, and the sum and zero numbers. But there's a different way, which is extremely useful, to look at matrix multiplication sometimes. So now let xi be the ith column of this matrix x, and yi be the ith column of y constant. Then also you can represent this product this way, as an outer product of 2 vectors. And here it's quite different, because the sum and the matrices, I'm adding together n matrices here, as opposed to a whole bunch of numbers. So how does this work? Well, here's 2 matrices, I'm just doing usual matrix multiplication. And I claim that this, when you multiply it out, it's the same as taking the outer product of this times this. So it's a, b, a, a, b, c, d, a. A bunch of 2 by 2 matrices that you add together. So this is very useful. And we'll use both of these tricks later, which is why I wanted to introduce them now. There's a quick and easy way to see why this is true, and that is just express this matrix as the sum of 2 matrices, right? That's perfectly fine. Express this matrix as the sum of 2 matrices, that's fine too. Then when you do the multiplication, this is non-zero only when it hits this. And that's what I mean by this. It's a shorthand for this and this. And essentially this only hits this, and this only hits this. So each column here only hits the corresponding row here. So we will use that in a little while. Just to make it abundantly clear, I'm going to use another trick, which the fancy name matrix invariant, but it's a really basic trick. It's always true if I have any matrix multiplication, there must be square matrices. If I add 2 and 2, I need the extent of 2 empty matrices. I can always add any column I like to the row on the left, divided by the single row of zeros in the corresponding row on the left. This will give me the same thing as this always. And again, we'll use this in a minute. But you can see immediately from this why it's true. If one of these is 0, so the population will lose. And the same is true if you just put the zeros here. There's no way to put the 0. But 0 here, y here, x here, 0 here. Okay. So that's some very basic matrix stuff. Now to some kind of useful tricks. I don't know about you, but when I was in college, I had to learn these horrible vector identities like this and memorize these things for physics. So this is a vector product of 2 vectors and 3 vectors. A vector product E. Just memorize all this stuff and it's painful and nasty. Until I realized that there's only one thing actually you have to remember, to derive all these things quickly. And that's this identity here. Hey, what's this? It's a low isometer antisymmetric tensor. It's just, what it is 1, if I, j, k are an even permutation of 1, 2, 3. It's -1 if it's an odd permutation of 1, 2, 3, and it's 0 otherwise. Probably all series, right? So I can expand this out this way, just by going through and figuring out when this is not 0. So then if I'm asking a vector like this, I can just expand it out using this form. Because A back B is epsilon ijk, aj, ek, that's what this is. Stick that in and boom, I've got my result. So derive, I always try to derive things rather than remember things on the bad memory, so I've much rather than what's in here and all these vector identities. So that's just one, probably you know that. But we can actually use it, the same kind of thing, to characterize both the determinant and the inverse of a matrix. So let's just look at that for a second. You've got some square matrix, A, n rows, n columns. Then the determinant you can define this way. N is the size of the matrix, the order matrix. This is the extension of the symbol I just showed you. Again, it's 1 if this is an even permutation, 1, 2, 3, 4, 5, up to n. -1 if it's an odd, 0 otherwise. And again, I'm summing on repeated indices. So alpha 1 is summed over, alpha 2 is summed over, beta, everything's summed over. It's kind of cool because it gives you an analytic expression for the determinant which you can then plug in and prove interesting things. And in fact, just a little puzzle for you. Remember my puzzle for being green? So you can show that this is equivalent to this. You get rid of the factorial and just stick 1 here, 2 here, up to n there. So it's a total antisymmetric sum of products of the A's. The Hilbert theorem will prove in 2 lines using this notation. Think of the matrix A as consisting of independent variables. Every element of the matrix is an independent variable. So I can do things like take derivatives on it with respect to that variable. So I can imagine taking the log of the determinant of A and taking the derivative with respect to Aij. By the way, all this stuff will actually be used. It's not just random. And the theorem states that that's equal to the inverse of A, transpose. Okay, how do we prove that? Well, we've got this here. So let's take the derivative with respect to each component. We'll just call the components ij. So take the derivative with respect to this, and I must be 1. Right, so let's take delta I1. This is delta 1, it's use the same 0 right? And j must be alpha 1. So I put j there as alpha 1. So the first term, I get n terms, right? If I take these n things, here's my n terms. And now I'm just going to multiply both sides by a, k, j, if you can do that, and sum over j, People indices are sum. And I get n terms again. But now, actually, only one of these terms is ever non-zero, because you can't have I equals 1 and I equals 2 at the same time. I has to be something, right? So suppose I have 1, then that's 1. In fact, k must equal I, because if k is anything other than 1 here, then you've got a, suppose it's 2. You've got a 2 alpha 1, a 2 alpha 2. You've got an antisymmetric sum. So it kills it, will make it 0. So k has to be 1, because this is the one that survives. Which means that it must be proportional to delta ki. And only one of these terms survives, and that's the expression of the determinant. So lo and behold, I hope to see how powerful this kind of representation is. In 2 lines, it's given us an 8. Okay. Let's characterize the inverse in a similar way. So the inverse can be rather similarly represented as this determinant. Well, again, some level in alphas, but not some level j and I. It's actually a constant here. And some of the alphas and is here. So now there's a little puzzle for you to do, which is check that this is true by just plugging in the expression for the determinant here. This expression is like here. And checking it, you get this. And one more theorem before we go on. This one's much easier to do. Again, I can think of the matrix as a matrix of variables. I can take and again, nothing is sum. It's very easy to prove this. You just use this, take the derivatives to both sides, that balance and make it incredible. Alright, how might one use these things? I'll just give you one example. Let's find the maximum likelihood mean and covariance of the Gaussian distribution in one slide using these theorems. So I have a Gaussian distribution. This is the Gaussian distribution in one dimension, actually an n dimension. Okay. And now I'm going to give you n points, and I'm going to assume that they're identically distributed, they're distributed from this Gaussian here, and they're independent points, independently selected from this distribution, and that means that I can express this as the sum. That's the product of the individual x's. Okay? So now if I take this and take the derivative with respect to the mean vector mu, and plug that into here, I get this. Right? And these sort of recollect themselves, some of the stuff left over when you get the derivative. And that means that this comes outside the sum, and so mean must be just sample mean. Well, that part is easy. You can actually use any of these theorems here. What about the covariance? What's the maximum likelihood of covariance? Well, now we're going to do our trick of taking the derivative with respect to components of the covariance matrix. So there's two terms. The covariance matrix here, this one here. And you take the derivative and set it equal to 0. You get to this must equal this. So A and B are not summed over. Alpha and beta are summed over. And I is also labels these vectors and vectors. So if I've got this, I can plug in my formula for d log determined by this thing here. Okay? And I just replace that with this. And lo and behold, I have an inverse guy each sum on the output table. If I signal both sides, and I get that the sample covariance matrix is indeed the maximum likelihood estimate of the covariance matrix itself. It's just an example, show you how things like this can be handled. Okay. So now we're going to do singular value equal, which means sometimes not draw from a course to this extremely useful. What is it? It's really a generalization of eigen decomposition. You can singular value decompose any matrix. So we're going to deal with arbitrary non-square matrices, A, M, N. And we're going to assume that M is just equal to N, although it works the way around too. So what I want to try and do is, it's very easy to sort of read a book on SVD and see everything works, but to get a visceral understanding of what's really happening, and some useful things at the end that you can easily compute with, it's a little trick here. So I'm going to try in 2 slides and 7 steps to give you SVD for its glory. Okay. First thing is, you can't have eigenvalues and eigenvectors in a non-square matrix, but you can imagine computing this object here, A transpose for any matrix A. Well, that we know how to handle. That's easy. It's positive definite, right? So that means that all its eigenvalues are positive, or 0. I is in Rn, yeah? This is square matrix now. All is positive, and it's positive, this is positive definite. So, basic idea is this. We don't know how to deal with A, but we do know how to deal with A transpose. We do know how to deal with A transpose A. So let's play with those guys and see if we can expand A in terms of eigenvectors of this guy. So the first step is to notice that A transpose has the same non-zero eigenvectors as A transpose A. This is trivial? Not really. They have different dimensions. This is n by n, and this is n by n. Let's prove it. Introduce a vector y equal to this, but these are the eigenvectors that I've got here. So the xi of the right singular vector A. Okay, I can certainly do that. Then if you just plug in A transpose A y, stick this in here, the y, you get this. But I know that A transpose A x is sigma squared x. And the sigma squared fits this in here. Sigma outside the whole thing is sigma squared y. So in fact, I've constructed the eigenvectors of A transpose A, and I've proven to you that at least for the non-zero singular values, or eigenvalues in this case, A transpose A, they're the same. Here's a little exercise. You can certainly choose the xi, these eigenvectors of A transpose to be orthonormal, because they're the eigenvectors of symmetric matrix. Well, if you know that they're orthonormal, here's the exercise, prove that the yi are also an orthonormal set. There's the same number of each, right? Now here's a theorem which is going to pull out of thin air. It's kind of mysterious, I think, but suppose you've got a matrix, arbitrary non-square matrix. Suppose it has rank k, maximum number of linearly independent rows, and it's also equal to the maximum number of linearly independent columns. So the rank of A is equal to the rank of A transpose. That's what I mean by what I say. But it's also equal to the rank of A transpose. And it's also equal to the rank of A transpose A. And I'm going to call the rank K. So think of rank K, if you pick up the indices are, okay? So there's the first 3 steps. Now what we're going to do in the next 4 steps, we're going to get to somewhere nice, and we're going to go in 2 directions. Some people want to do other things in terms of matrices, some people want to do other things in terms of products, so let's do both. So now I'm going to form a matrix of the columns of the y's and the x, just like the eigenvector matrix for eigenvalue decomposition. And now x is in nk, where k is the rank of n. And y is in nk, and don't forget n is bigger than or equal to n. And by definition, remember I defined the y's as space, it's just a matrix formed of the definition of the yi's. Well, this guy certainly has an inverse. What I mean by this is a diagonal matrix whose diagonal elements are 1 over sigma 1, 1 over sigma 2, 1 over sigma k. So that has an inverse because they're all positive. So apply the inverse to both sides. So now, if it's a square matrix, we're done because because then this is orthonormal, right? So I can apply x to both sides and I get this. But the problem is it's not a square matrix. So now if n is less, there's 2 things that can happen. N, the number of rows of A can be less than the rank or equal to the rank. So what we can do is, if n is less than k, we're going to add a bunch of rows to the bottom of x transpose here. Because we want to be able to take the inverse. We want to make it square. So we want to add orthonormal rows to the bottom so we can just take the inverse on both sides. How do we choose those orthonormal rows? If we choose them to be orthogonal to A, it's not going to make any difference. We multiply it and get 0. So that's fine. So I can add zeros to this matrix now, so it's no longer diagonal. It's diagonal, it's got rows and zeros at the bottom. So now we're going to construct a unitary x, or a orthogonal x, to be honest. Okay. And now, superb, wonderful, we can take the inverse. We've got this thing, and just like instruction, I've made x into an orthogonal matrix. There's one trick here that's an exercise for you, and that's to show that x is actually unitary. The only step I haven't explained is, if I add these magnetic orthonormal vectors to the bottom of x, you've got to show that they're also orthogonal to to all the other rows. They're certainly orthogonal to each other by construction. And the first set of rows are orthogonal by construction. But you actually get it's very easy to simplify on that view. So now we're in business. Now we have something very like SVD, but not quite. We have, so matrix A, we have a decomposition. Let's look at what spaces these matrices live in. X is square, it's m by n, that's nice. This is kind of weird. It's diagonals with a bunch of zeros, but this is not square. And so we're not really in sort of useful matrix now, because we like to take inverses of the y's too. So there's two directions we can go. The first direction is to do the same trick, add things to the y's to make it unitary. So if you want something close to the eigendecomposition in terms of matrices, we're going to add a bunch of rows to the yi, corresponding by transpose. And corresponding columns, remember that trick I told you about adding any rows you like, as long as you have zeros. Then we've made y unitary also. And now we're really in this. This is the SVD, okay? By applying sigma I 0, 0, I mean a diagonal matrix whose diagonal elements are sigmas. There's a bunch of rows of zeros added to make x squared, and a bunch of columns of zeros added to make y squared. So it's not anymore square matrix. But now x and y both are square matrices. So now it's great, because I can take inverses of x and inverses of y. I just have this slightly odd thing in between them, which is not square. A bunch of zeros at one, a bunch of zeros on the side. Well, that's one direction you can go. And this is the SVD effect. But another direction you can go, which is very useful in calculations, is to forget matrices when it's weird adding rows and stuff, and just get sort of the meat of the matter. So we want something closer to our product. So we got to here, right? We got to here by a trick, by adding rows to x and columns to by sigma. Columns to x and rows to by sigma. So now we're going to get rid of those rows. It was just a trick, actually, got to take the inverse, get them here and here. Now we're going to say, okay, well now I can get rid of them. They don't do anything, so there's these zeros here anyway. If you do that, you get this. It's a very nice, it's sort of the minimal SVD decomposition of A. So what is it? These matrices, remember A is m by n. These guys are n vectors. This is our product I showed you before. These guys are m vectors. And there's only k elements in the sum, where k is the rank of A. It could be anything up to n, right? Because n is estimation of n. So here is probably, well, certainly as useful as this. Two different ways to look at SVD. Okay, so there's SVD in six steps. Let's start using it. We'll have to use it several times today. So we're trying to handle rectangular matrices. And one of the things you might want to do is have an inverse. But rectangular matrices can't have inverses. So let's get something close to an inverse. Remember that A is square and diagonalizable in an eigenvector decomposition. So this is orthogonal matrices. And if further A is on singular, it has an inverse, then the inverse is just this. Of course, if you multiply this by this, you get 1, this all cancels out. That inverse being one of the eigenvalues down the diagonal. These are eigenvalues. We'd like to do something like this, but for SVD. So is there an SVD-like generalization of the inverse for arbitrary matrices? And by the way, the more generalized generalized inverse, also called the pseudo-inverse in various places. But it's not the only pseudo-inverse. There's lots of ways to define pseudo-inverse. It's one people use most, I think, in our next videos. So now we've got this. Now this is the SVD of A. I'm just reminding you where things live. This is unitary, n by n, unitary, n by n, diagonal, so not square though. So now I'm going to define this strange A dagger object, where I'm going to switch these guys, like I switch these guys. It's just like this. I switch these guys around, right? And I'm going to replace each sigma by one of the sigmas. Don't forget all the sigmas are non-zero. And now it's actually an nn. It's in the same, it has the same dimensions as the transpose effect. Here is the simple way to remember it. Remember we had A is sigma x y transpose. Swap the x and the y, replace sigma by one over sigma. Again, this is now product, a very simple form of this inverse. Generalized inverse. So it has some nice properties. First of all, A dagger A and A dagger, and A dagger for dimension matrices. And I think they're symmetric. I'm dealing with real matrices mostly, but this one is a complex too. So why is this called an inverse? Well, this is true. I mean, these are exercises. Just plug it in. It's a line of work. Say A dagger operating on A is like the unit matrix operating on A. So in that sense, this is the unit matrix, one that operates on A. So in that sense, A dagger is the inverse of A. And A dagger gives you A dagger back. So this is like the unit matrix operating on A dagger from the right. So it's a bit like an inverse in that sense. In certain matrices, it looks just like an inverse. Interestingly, if you require these conditions, then say what condition matrix, matrix A dagger gives you this, you get the four-period generalized inverse. Now, a few points about it. If it's square and non-singular, then as we hope, it actually is the same thing as the inverse. It's just square, isn't it? You want to generalize inverse well down to the regular inverse. Now, it may be true that it's singular, A is singular. But it may also, it may be true that the A transpose A inverse exists, even though A is not square. Okay? So if A is not square, you can't think it's inverse, but you can form this. This may have an inverse. If that's the case in this explicit form like this for A dagger. Although A dagger certainly, you can write it down even if this doesn't exist. It's completely general. The same is true if A transpose inverse exists, so there's another way to write this. Okay, we'll use A for this in a second. Let's start. First, I have to just go and range the null space of the matrix. So remember, A, this matrix, this rectangular matrix, is in this NN space. What's the range of it? Just the space that it maps to. So you take any X, you plug it in, you get a bunch of Y's. Whatever those Y's span, that's the range of A. It's a linear map. The null space is a lot different. It's those vectors upon which, when you act with A, you get 0. So this is a different space. These are n vectors, these are n vectors, n less than n. That's the definition of range agnostic. Now, let's think about that. Remember this expansion I showed you earlier? If A dot I are the columns of A, then A matrix I can represent this way, right? These are just vectors. And AX can be written as x1 times the first column plus x2 times the second column. It's also a very useful way to think of vector matrix multiplication. And that means that the range of A must be spanned by these vectors, because it's just a linear combination of A. So that means that the dimension of the range must be the rank of A, the number of linearly independent columns. Okay? Similarly, the null space of A transpose is spanned by those vectors on front of every row of A transpose. So take A transpose, zap it on an X, you want it to be 0. So that means that the rows of A transpose have to be orthogonal to your X's. So we're looking for those vectors that are orthogonal to every column of A, every row of A transpose. And that means that the range of A is equal to the orthogonal complement of the null space of A transpose. So we've got two different spaces here. The range of A is Rn. The null space of A is Rn. But this holds. So they're very closely related. One more word on range and null space. The dimension of the null space of a matrix is the number of linearly independent vectors that are orthogonal to every row. And you've got a zap to 0 whenever you get something in the null space. Okay? And the row vectors in A are in Rn. So I'm looking for all vectors which are orthogonal to a bunch of vectors in Rn. And that means that the dimension of this null space is the dimension of the space I'm in minus the number of linearly independent vectors I have to be orthogonal to. And so we get this crucial identity here. For any n by n matrix, the row columns is n. The dimension of the range of A added to the dimension of the null space of A is n. Keep any matrix. Let's see that using our SVD, our sort of minimal SVD. So here's our SVD of A. So the null space is going to be anything that this is orthogonal to all the y's, right? If I zap this and goes to z, I've got a y transpose hitting a z. If that's always 0, then z is in the null space of A. So it's the null space is a subspace orthogonal to the k y's, the k of them, this is my k. So it must be the dimension n minus k. That's a quick way to see that. Similarly, the range of A is spanned by these x's. So this dimension is just the number of x's, which is the rank of A again. slid something into the rug as an exercise for you. Suppose that even though I choose a z, I multiply by a, it's not orthogonal to all of them i's, why couldn't it be that this alpha product still sums to 0? It must, actually, it cannot sum to 0, in fact, if z is not orthogonal to all these. So why is that? It's an exercise for you. Okay, so now that we've got range and null space down, we can characterize the maps using SVD. So what are you going to do? People often do stuff like this, so let's go through this carefully. I have some sort of a linear system I want to solve. A is in n by n, B is in Rn, and B is in Rn. It has 0 or relatively many solutions. Of course, it has two solutions, and linear combination is not a solution, so this is why it's one infinity. When does a solution exist? Well, we know that AZ, as I just showed you, is a linear combination of the columns of A. So B had better be in that space, right? It's better in the range of A, or this solution exists at all. In fact, if B is in the range, then this is the solution. And you can see, just to show you how powerful this SVD decomposition is with this for minimal version, so right away, A, Z0, Z0, is A dagger, there's my SVD of A, there's my SVD of A dagger. Y is orthogonal, so that gives you a drop function. One of these sums disappears. I get this, these are orthogonal to get B back. And the general solution then to this problem is Z is the generalized raw temporose inverse acting on B plus the null space. I can always add a null space sections, and A acting on that would give 0, so I can add anything in the null space. So this is the general solution of this system of equations. But it might well be, since we always use computers, that this isn't quite true, that there's no B that quite satisfies this, right? It might be that B is outside of the range of A, numerical problems, something like that. So what happens if that's true? If there's no solution, no exact solution, but you want the closest to document case. So what you'd like to do is first of all minimize this square, say with Euclidean norm. Find the Z that makes this as small as possible. But given that, there's a whole bunch of other Z's because I can always add to the null space, a vector to the null space, and get the same AZ, right? Because they just zap it to 0. So I want to minimize this, and within the solutions that minimize that, I want to find the one with the smallest length. The solution to this problem is, again, just a generalized inverse. So this generalized inverse is pretty handy. It solves the approximate problem as well as the exact problem. Let's get on to quadratic programming, just a little example of how this might be used. You're faced with this problem. Here's your function, here's your objective function, you want to minimize this. And this is your objective function. A is positive semi-definite by this, I mean positive semi-definite. And X is an Rn. Well, it's unconstrained, right? So I can just say the gradient was Spanish. The gradient was Spanish, I can do this, use SVD, have all the solutions. So first of all, if B is not in the range of A, there's no solution. Well, you might think, I can always try and find a solution, why not? So to complicate this little puzzle for you, suppose B is not in the range of A, there's no solution to this. But you try and minimize this anyway. What goes wrong? What happens? Why is there no solution? Okay. So if B is not in the range of A, there's no solution. Else the general solution is just this. It's the SVD solution to this equation. It's a very simple, unconstrained quadratic programming problem. And SVDs help us solve it very clearly. SVD is also related to matrix norms. Let's talk about matrix norms for a second. Remember, a norm is defined to be as follows. For any object in a vector space, and these certainly live in a vector space, right? I can add them, I can multiply them by scales. So the norm is a map from my matrix to just the numbers, such that for any A, B in the space, the usual norm conditions hold. It's always going to be positive, it's 0 if the economy of A itself is every 0, every element is 0. Multiply by a scalar, the scalar comes outside, that's the magnitude, and the famous triangle inequality. Okay, it's just regular norms, whatever the norm is. Now, if the unit sphere, the unit sphere of the P norm. And I ask for the maximum. Now this is a vector, right? So I can compute P norm. And I ask for this to be maximized. Then I can define that to be the P norm of the matrix A. So now I've got a way of computing P norms and matrices. And they kind of hang together kind of interestingly. It's a very famous norm people use a lot when they try to approximate things. When they want something to be close to something else. It requires that the Frobenius distance is as small as possible. And what's the Frobenius norm? It's actually kind of brain dead. It's just the sum of the elements squared for the real matrix. Why could that be useful? It seems like so obvious. But this is the Frobenius norm of a matrix. It's also equal to the place of A transpose A, as you can see. And that means that it's equal to the sum of the sizes of each column of A. Okay? So one thing that's nice about A is, about this norm, is that it's invariant on the unitary transformation. Like you take A by orthogonal A, orthogonal transpose, has the same Frobenius norm. That's kind of nice. Another interesting property, which is an exercise to propose. Suppose you take an arbitrary orthogonal basis, not the usual 1, 0, 0, 0, 1, 0, all that, but some arbitrary basis, but this is orthogonal. The Frobenius norm can also be written this way. This 2 means it's the Euclidean norm, it's just the square of the Euclidean norm. And prove that. It's very easy, but prove that. Here's an interesting thing. Remember I derived a matrix norm from a vector norm. So remember the vector norm for the L1 norm is just the sum of the components of the vector. That's the magnitude. What's that turn into the matrix? It's actually a max column norm. You take a given column, you fix it, you sum over all the rows, taking the absolute magnitude. So think of a matrix, you sum over each row, you replace the top row with just the sum. And you get the max of those numbers. That's actually the L1 norm of this matrix A. How about the L infinity norm? Well, it turns out that's just the same thing, but you're doing it on rows. So I take each row and I sum the rows, and I find a max such sum. It's kind of weird. I mean, the L1 and the L infinity norm are not so obvious. Right? There's something called the spectral norm, which is just the Euclidean version of this. Okay, D equals 2. And here's where a CD comes in. It's equal to the largest singular value. I ordered my singular values where the number 1 is the biggest and the n is the smallest. And in fact, the Frobenius norm has an SVD expression too. It's just the sum of the singular values squared. Note that there's only k of these guys, but this could have rank k is less than either the number of columns or the number of rows. One more point before we leave norms, and that is, this is a max, okay? Suppose I take the min instead. I've got my AX Euclidean norm, and I ask for this. Then it turns out you can write this expression in terms of the smallest singular value, where I've used notation. This is now sigma n. N is the number of rows of A. So it could be 0. Obviously it could be 0 based on all states, right? So it just gives you an SVD. If it's not 0, then it's a singular value of the matrix. This is not a norm, it's just something you might want to compute sometime. And there it is in terms of the SVD. Okay, tricks of positive similar matrices. People use these properties in their matrices all the time. Are there sort of properties that you can use and remember about them that are useful? So, a matrix is positive semi-definite, by definition, it's symmetric for real matrices, and this is true. And it's positive definite, this is always going about, right? And there's that. So let's look at some properties of positive definite. Let's just gather them together. All diagonal elements must be positive. For positive semi-definite, and it must be greater than 0, strictly greater than 0, it's positive definite. This is not the eigenvalues, this is diagonal elements, so that's a useful thing. If every diagonal element is equal to 1, then every element must have size less than or equal to 1. We're going to prove all this in a second, and it's incredibly easy when you use a trick that I'll show you. Okay? So you don't have to remember it essentially, but you can prove it so easily. A is positive semi-definite in rank 1 means it must be of an out product form for a single vector x. There must be some x, such that A is xx transpose. In fact, I think it's true for rank 2 is xx is something that x transpose plus x is y transpose and so forth. If A be a positive semi-definite, then you can multiply them. They have the same size, then so is AB. Here's an odd one. A is symmetric, and A is an anti-symmetric matrix. All leading principal minors are greater than 0. What's a principal minor? Take the top left element, that's going to be greater than 0. The determinant of the top 2 by 2 matrix, top left 2 by 2 matrix, so it's going to be greater than 0. Top 3 by 2 matrix, they want to be greater than 0. This does not work, by the way. This is greater or equal to 0. This is greater or equal to 0 is not necessarily positive semi-definite. Easy kind of example for that. And finally, something called diagonal dominance in matrices just means that the diagonal element is bigger than the sum of the row of all the elements. That is positive definite. Let me give you a couple you may not have seen in the books. Here's a pretty easy one. If any element, so this is partly tricks of the semi-definite matrix, and it shows you a matrix that says, this is semi-definite, you say, no, because bang. So here's one. If one of the diagonals is 0, then every element in the cross-line row and column must also vanish if it's positive semi-definite. Here's one that most people don't have, I think. Suppose you've got a positive semi-definite matrix, and you choose some element off the diagonal, and then you look back to the cross-oriented diagonal elements, which are just called Y, Z, and X here. And if this is violated, this matrix cannot be positive semi-definite. All we have to do is find one element that violates this and bang, and then you've got a matrix that's not positive semi-definite. Alright, so these might seem a little strange, but you can prove them incredibly easily once you know this theorem. So suppose you've got a vector space over some field with some inner product. The ground matrix is something that people have been using ground matrices, the strong background matrices. But the set of vectors in this vector space, in an n of them, is defined to be this. This is the inner product. So it's an n by n matrix, right? Here's the theorem. A is symmetric, n by n, and it's positive semi-definite if with rank R, that's equal to n. If and only if there's some set of n vectors containing exactly R independent vectors, such that A is this ground matrix of these vectors. There's two things here. There are two sort of theorems for ground matrix. The first is every positive semi-definite matrix is a ground matrix, every ground matrix is a positive semi-definite. The second is that if I give you a positive semi-definite matrix and it has rank R, then the number of linearly independent vectors you need to construct it as a ground matrix is R. If you need n vectors, which you need R to be independent. Okay? So let's prove that remember this last weird sort of party theorem, party trick theorem. Let's prove these two. First of all, I claim this is positive semi-definite. Is it really? Oh, there's a 0 there. Okay, if there's a 0 there, this must be xi dot xi, some xi, right? This is also a ground matrix. And this is xi dot xj, some xj. But xi squared is 0, so this must also be 0, as demonstrated here. Everybody see that? Oh, I get that so quickly. This is a ground matrix. Diagonal elements are just vi dot vi. If that's 0, then vi itself must be 0. So it's not that anything else must be 0, which means that the row and the column must be 0. Okay? What about the other one? Well, that's easy to see too. I choose x, and I claim that this must be true as long as this is positive semi-definite. But I know that if this is x, a use notation, I call it xi squared, that's xj squared. This is xi dot xj, just using a usual British Schwartz. Yeah, that's what you do. That's just what you want. So there is a proof in one line of this theorem. If you ever are given a positive semi-definite matrix, and you notice that this guy is bigger than these guys, you can say, no, it isn't. Not true. Now, it's actually useful sometimes to work with these ground vectors. I'll give you a positive semi-definite matrix. You can compute the rank, so you know how many independent vectors there are. But how do you actually get the vectors? Because then you can do calculations easily. Okay? So now, here's A. I'm going to eigendecompose it. This is the orthonormal matrix of the eigenvectors of A, labeled by J, so it's vectors of components. It's just this written out with components where repeated as indices of sum, and this is written out again. Now we're summing on vectors, taking the aggregate component, but we have this magic dual, right? Summing on vectors is tricky, I don't know what that means, but I want to sum on components. So I'm going to define a new vector by just scaling the eigenvectors. Then Aij is just this, right? Sum of components. But then I can compute the dual, where the components become the names of the vectors and the names of the vectors become the components. You switch. Now I've got a simple dot product. So the ground vectors on the dual basis to the scale eigenvectors. So you can get these like that. And that's pretty handy. last thing on matrices, then I'll stop. People use this a lot also in machine learning. I give you a symmetric matrix, okay? And I ask you to do Euclidean distance. What's Euclidean distance? It's a matrix of distances between data points. So I might give you a bunch of data. You can put the distance between each point. I'm actually defining this to be Euclidean distance squared. Some people can also define it as a square. And that's obviously useful where you can stuff on eigenmaps and structure clustering and all that kind of stuff uses this. What is a symmetric matrix? Euclidean distance matrix. So give you a symmetric matrix. When is it like this? When can you find x's in this like this? Well, clearly the diagonal limits have vanish, right? That's not true. It can't be at this point. So here's the theorem. D is in a space of symmetric n by n matrices. Is a Euclidean distance matrix. Some points in our K, or some K, if that's what K is. If and only if the diagonal vanishes, and for all y satisfying y orthogonal unit vector, I mean vector of all ones, this is negative semi-definite. It's an old theorem, actually. I tried to dig up the proof on this paper so I couldn't get the paper. So everybody knows this theorem, and it sounds well known, but they don't actually write it. But we can actually, the proof one way is very simple, so let's look at that. Let's suppose I give you a Euclidean distance matrix. Let's see why this must be true. Okay, so here is my Euclidean distance matrix. I've just expanded out the norm, right? Take this, expand this out. Now, compute this in this thing here. That's what this is with those components. Well, y, these are labeling vectors. These are just components of the vector. So the x i's are vectors, y i's are components of y. That gives me this, but I sum over yj, so j term here. Same thing happens here. And then I get this. Okay. Well, if I require this, then the sum of the yi is 0. So that vanishes, and I'm left with this, which means that it's negative indefinite. It's always a negative constant because it's the square of weighted vectors. So we've just proved in one line part of the theorem. That's not possible. Okay, we're going to look at it and start with that. So next, complex optimization.